In this second lesson on the binomial distribution, I want to go through 3 ways that binomial distribution problems can become more advanced or complicated. The first of them is by hiding the number of trials and the probability of individual success. You may have noticed in the last video that it was pretty clear how many trials there were and what the probability of success was. And there are definitely ways that the problems can sort of hide that and you have to find it. The second way is by asking you to compute conditional probabilities on binomial distributions, so doing that whole restriction of the sample space. And a third way is that they can take other probability problems that are not binomial and then turn them into a binomial distribution problem at the end of the problem. So before we get deeper into this, let's go ahead and take a deep breath. And let's continue our learning. This slide might look a little bit daunting with all these symbols jumping at you, but I assure you it's really straightforward. So first, recall. We learned in an earlier lesson, a little while ago, that we can find the expectation and the variance of a discrete random variable by using these equations. Okay, we learned that the expectation is found by just multiplying the the value of the variable times the probability of that variable. Just realized I've got a little typo here. That right there should say the probability of x equals x. Sorry about that. So that's how we find expectation. And variance we found by doing this, the mean of the squares minus the square of the mean. So cool. That's great for discrete random variables. The binomial distribution is a discrete distribution, but good news. When we know that a random variable is distributed binomially, these things are way easier to compute. If you want to find the expectation of the random variable, the expected number of successes, all you have to do is multiply together the number of trials with the probability of success. That's it. Okay. If you know that a variable is binomial, the variance is also really easy. For the variance, all you have to do is multiply together the number of trials with the probability of success with 1 minus the probability of success, which is basically the probability of failure. So these you can use for any discrete random variable, but if it is binomial, then it's way easier to do. Okay. Now, these formulas are in the formula book, and remember, you're going to get that formula book on the IB exam, so you don't need to memorize these, but they really are quite straightforward. So this first style of problem is, again, going to sort of hide the idea of the number of trials and the probability of individual success. So they might do this by just, stating really, really clearly, x is distributed binomially with some unknown number of trials and unknown individual probability of success. Then they tell you that the expectation is 1.2 and the variance is 0.96. So for part A, they might now ask, hey, all right, cool. So what are the values of n and p? How could we find out what those things are? And you'll notice it's not like you can just plug this into Binomial PDF and find it out. You're going to need to think about how to do this. Okay? Well, we know from the previous slide that the expectation, E of x, is supposed to be equal to n times p, and that's supposed to be 1.2. Okay? Further, we know that the variance for a binomial distribution is supposed to be n times p times 1 minus p, and that should be 0.96 for this problem. Okay, well, look at what we have here, right? And we shouldn't have been surprised. They were asking for 2 unknowns. Anytime they're asking for 2 unknowns, it's going to be a system. I now have 2 equations with 2 unknowns. So now I'm going to do this really sneaky thing. If NP is 1.2, let's just put that right here where it says NP. So I'm just going to take this 1.2 and put it right there. So 1.2 times 1 minus p is 0.96. Okay. So we can use our calculator here to divide 0.96 by 1.2. And I'm finding that 1 minus p is 0.8, which means that p must be 0.2. Okay, so I just found out what p was. Now I can plug it back in. N times 0.2 is 1.2. Again, dividing this, 1.2 divided by 0.2 gets me 6. So we just found out, all right, cool. If the expectation is going to be 1.2 and the variance needs to be 0.96, the number of trials must have been 6, and the individual probability of success must have been 0.2. Okay. Now that I have those two things, this problem becomes exactly like everything we did in the previous lesson, right? So for problem B, where they say hence find the value of p of x equals 2, what are you going to do in the calculator to help you with that? Hopefully you recognize that this is going to be you doing Binomial PDF. By the way, why are we using PDF instead of CDF? Hopefully you recognize we use PDF because it's asking for one individual probability, right? So I'm going to go ahead and go Binomial PDF. I'm going to say that there are 6 trials. Individual probability of success is 0.2, and the x value that we're asking about here is 2. It's 2 because that was the value that we went with here. When I plug all that into my calculator and have the thing run, it tells me that this is 0.246. So that's the probability of getting exactly 2 successes. Remember, I wrote the Binomial PDF over here in red because IB doesn't expect you to use calculator notation. Remember, they won't take points off for it, but they're also not going to give you any credit for it. Now, part C. Part C, they want me to find the probability that x is greater than 3. Now, do you remember how you're going to need to do this from the previous one? If you think you do, pause the video, try and write down what you think it's going to be, then we'll talk about it together. In my mind here, the probability of x being greater than 3, that means that out of a total of 6 trials, they want the probability of x being 4 or 5 or 6. And Binomial CDF doesn't do very well with being above something, so I want to rewrite this as being 1 minus. So what's the opposite of being 4 or bigger? Opposite of being 4 or bigger would be 3 or less. So I'm going to do x is less than or equal to 3. And now I can use my Binomial CDF on that. So from the calculator, I got that this was 1 minus 0.983, which means I wound up with 0.0170. I'll make a brief comment here that, again, it's worth thinking about reasonability. And I know that this is hard for some of you, but if I have 6 trials, it's a 20% chance of being successful on each one of them, and I know I'm only supposed to expect 1.2 successes out of 6, the probability of getting more than 3 successes should be pretty low, right? This idea of having like a 2-ish% chance shouldn't be super surprising to us. This problem should be really similar to the last one. There's a little catch here in that this is the standard deviation. So think for yourselves. Remember what the relationship is between standard deviation and variance? Right? We need to square the standard deviation to get the variance because we squared the variance to get the standard deviation. Pause the video, try and do this one on your own, and then we'll come together and we'll check it. All right, so for part A of this problem, finding the values of n and p, we know that the expectation, 9.6, should be np. And we know that the variance of this thing would be this squared. That's 5.76. So the variance, 5.76, should be n times p times 1 minus p. So just like we did in the previous problem, we'll take this and substitute it in for np. 5.76 equals 9.6 times 1 minus p. So when we divide this out, 5.76 divided by 9.6, I'm seeing this to be 0.6 equals 1 minus p. That means that p has to be 0.4. So we found one of our parameters. When I take that and plug it in over here, 9.6 equals n times 0.4. If I divide that over 9.6 divided by 0.4, this gives me 24. So I'm done with part A. I figured out what the parameters are. I figured out that there are 24 trials and the individual probability of success is 0.4. Okay. Now part B, they now want to know, hence find the value of x being greater than or equal to 9. And actually, before we do this, I want you to think for a moment. Think, like, should this be a larger probability or a smaller probability? You might sort of think to yourself, well, I'm expecting 9.6 successes out of 24, right? So I'm expecting more than 9 successes, and they want the probability being 9 or greater. This is probably going to be a largish probability. So we sort of go into it with this expectation that we're going to find a decent-sized probability. So they want the probability that my number of successes is greater than or equal to 9. So that would mean getting 9 successes or 10 or 11 or 12 or 13. Again, that doesn't work very well with binomial CDF. I want to do the opposite of that. I want to do 8, 7, 6, and on downward. So I'm going to do 1 minus the probability that x is less than or equal to 8. And now this is something that I can do with binomial CDF. I got this to be 1 minus 0.328, which means that my final answer ends up being 0.672. Remember, we were sort of expecting a decent-sized probability. 67%, it's bigger than 50%. Like, I feel good about this answer. One last comment here. I did both of these past examples as kind of like abstract problems where they just sort of started out with something like this. This problem could also have been set in a context. So it could have been something like, it is known that the number of times Ava eats at a restaurant over a period of time is binomially distributed. It's known that the expected number of times is 9.6 and the standard deviation is 2.4. So these problems could be as word problems, and we may see some of those in the assignment tonight. I just kind of wanted you to be exposed to this type of binomial complexity. So now we're moving on to the second way that these problems can be increased in complexity. Recall what we learned in the previous lesson about conditional probability. This would have probably been a couple weeks ago. When computing conditional probability, we always think of it as a restriction of the sample space to the condition. And in fact, we learned a formula for it, right? We learned this formula, and we even interpreted that formula. What this formula really does is the denominator restricts us to the sample space of just the condition where B has happened. Remember, this is the probability of A given B. So when we say given B, we're sort of saying the probability of B is the denominator. That's the sample space. And in the top, we're counting all of the places where A happens alongside B. I'm not counting any of A's that were outside of the realm of B. So we've done conditional probability before. We restrict ourselves to the sample space like this. I now want to talk about how can this formula be used in parallel with the binomial distribution. So let's get into some examples of this. This is another one of those things that can be a little complicated. So I want to start this problem like not doing the probability piece. I just want to do the conditional piece. So it says let R be the number of rainy days in San Diego in April. Oops, I just realized I had a little typo here that they should all be March. So let R be the number of rainy days in San Diego in March. Given that in 1 year it rained fewer than 10 days in March, write an expression to find the probability that it rained at least 7 days in March. Okay, so this thing is saying find the probability that and we've got R to be the number of rainy days. So find the probability that it rained at least 7 days in March. So find the probability that the rainy days, at least 7, that means 7 or more, so greater than or equal to 7. So what's the probability that rainy days is greater than or equal to 7, given what? Given that it rained fewer than 10 days. Now, fewer than 10 means not even 10. It means like 9 or fewer. So this is like R is less than or equal to 9. Okay, and if you didn't understand that, like slow down, pause, go back, look at this again, right? We want the probability that it rained at least 7 days, that R was greater than or equal to 7, given that there were fewer than 10 rainy days, so that R is less than or equal to 9. Now, I actually want to go one step beyond this. How would I do this in a formula? Right? What do I restrict my sample space to? And then what's the numerator? So first, what do I restrict my sample space to? I restrict my sample space to this, to the condition. On the bottom, I want the probability that R is less than or equal to 9. Okay? Now, what about on the top? Okay. On the top, I need it to be both greater than or equal to 7 and less than or equal to 9. Right? So wouldn't I do something up here like the probability that 7 is less than or equal to R is less than or equal to 9? And again, I want you to sort of like slow down, pause, think about that for a moment, right? This is saying R has to be less than or equal to 9, and I want to know the probability that R is greater than or equal to 7. So basically, R's got to be in between 7 and 9. So I'm hoping the setup for that made sense. What I'd like to do now is I'd like to sort of add some numbers to this example so that we can practice like actually computing this. So suppose that now I go on and tell you that the chance of it raining on any given day in April keeps showing up again, in March, in San Diego is 15%. Okay? Compute the probability that you expressed in the previous example. So it's kind of like, now that I know that rainy days are distributed binomially with 30 days in, oh wait, we're in March, so 31 days in March, and an individual probability of chance of 0.15. Now that we have that, how will I carry out these things here? Hopefully you recognize that one of these is really easy and the other one is a little bit complicated, right? Shouldn't the bottom just be a really easy, like binom CDF, right? The top one is where we're going to need to think a little bit more, right? If I want to find the probabilities that are only between 7 and 9, I could either do binom PDF for 7, 8, and 9, or I could kind of do a sneaky thing here, right? I'm going to write this down, and I want you to sort of like pause the video and see if you can make sense of it. What I could do in the top is I could do this. R is less than or equal to 9 minus the probability that R is less than or equal to 6. And I want you to, again, pause the video, think about why that would make sense on the top. So do you see how, like, this would give me the probability of being less than or equal to 9, and then this would take away all of the probabilities of being 6 or lower, which would leave me with just the 7, 8, and 9 probabilities. Okay. So that's kind of how I got this thing and how I express this. There will be a chance for you to practice on the next page. At this point, you would just do these three things as binom CDFs. So I'm going to go ahead and run those in the calculator and write out what our answer is. So on the calculator, I got these to be 0.988 minus 0.827 divided that by that same 0.988. And then when I divided that out, I got 0.163. Again, taking like 20 seconds to check for reasonability here, right? We expect, so there are supposed to be 15% of the days are rainy days. So out of 31 days, that 15% of 30, it's like 4.5 or 5 days, okay? So like getting fewer than 9 or fewer rainy days, that's a lot of it, right? In those, having 7 or more rainy days, at least 7, like that's not gonna happen very much. We're expecting like 4 or 5, I mean, maybe 6. There's going to be even fewer than that. So it's not surprising that this is sort of a small chance. That if it happens to be that rainy, that there's really a lot of them. I know that's confusing to see, but I'm going to try and keep bringing it up so you get a chance to hear it and see it yourselves. So here's one that should be fairly similar to the previous problem, and I want to give you guys a chance to kind of try it on your own. These can sometimes be confusing, especially when there's dice, because there's just a bunch of numbers floating around. A fair 6-sided die is cast 20 times. Given that the die came up 5 at least 2 times, find the probability that no more than 4 5s were obtained. Especially when things are complicated like this, I think that there's a lot of value in using some of the steps that I talked about in the previous lesson, right? So starting out with like a definition of the random variable. So again, I start by picking this capital letter. Let F be the number of 5s rolled on a fair 6-sided die in 20 throws. Okay. The next step isn't super necessary, but stating that F is distributed binomially. Oops, got the wrong thing there. F is distributed binomially with 20 trials and an individual probability of success of 1/6. Now, this is saying, given that the die came up 5 at least 2 times, find the probability that no more than 4 5s were obtained. So again, I think it's valuable for us to try and write down, this was step 1, this is step 2. Step 3 is where I write down the probability I want to find. I want the probability of getting, let's see here, find the probability that no more than 4 5s, no more than 5. So not more than 5. So I'm sorry, not more than 4 5s. You see how it's like hard because these numbers are random? So not more than 4 5s. So I can't get 5 5s, I can't get 6 5s, I can't get 7 5s, I can't get 8. So no more than 4. So that would be 4 or 3 or 2 or 1. Some of you might have been upset that I kept saying those things. I personally get confused when I do this. Like this thing I'm doing is not like for you, it's in the lesson. This is me pulling apart what's happening in this problem. So no more than 4 5s means this. So they want the probability that my number of 5s is less than or equal to 4, given that the die came up 5 at least 2 times. At least 2 times. That means 2 or 3 or 4. Okay, so that means given that f was greater than or equal to 2. Okay? So now I've got an expression for, remember, all of this stuff that you're writing, this is all partial credit. So even if you mess up the rest of the stuff, if you're able to do this, you're going to get points on the problem. Okay? So now I need to figure out what the equation for this thing is, right? Now when I do this thing, remember that my denominator is where I'm restricting myself to the sample space. So the probability that f is greater than or equal to 2. In the numerator, I need where both of these things happen. So where f is greater than or equal to 2 and f is less than or equal to 4. So I'm going to have the probability that 2 is less than or equal to f is less than or equal to 4. Okay. Now, if you haven't done much of the problem to this point, maybe see if you can break apart the next part on your own. The numerator here will be the probability that f is less than or equal to 4 minus the probability that f is less than or equal to 1. And then in the denominator, I'm going to have the probability that f is greater than or equal to 2. Remember again why the top makes sense. We wanted to count all the stuff that was like 2, 3, and 4. So I'm counting everything up to 4, and then I'm hacking off anything less than or equal to 1. At this point, I find these 3 things in the calculator, and I do that computation. So I got these things to be 0.769 minus 0.130, sorry I ran out of space there, divided by 0.870, and this wound up being 0.734. So we've now done 2 examples of problems where conditional probability and the binomial distribution can interact with one another. For the third type of complication, you can start with a problem that's not binomial at all, like a tree diagram or a Venn diagram. And then at the end, the problem mentions that that trial probability that you just did is going to be repeated multiple times, which sounds a lot like a binomial distribution. So I only have one example of this one, although this is something that comes up on the IB exam quite often. So it's something we definitely want to be prepared for. As we start this problem, remember, many of the questions on IB exams are long questions, multi-part questions, and those parts are almost always connected to one another. And so, as I pointed out before, commonly on the IB exam, when you've got a long probability question, one of the last parts will be a binomial distribution problem. So we're going to see that happen here. So for this example, the breakfast that I cook for myself on any given day depends on whether or not I get up on time. If I wake up on time, there's a 70% chance I'll cook chilaquiles. Otherwise, I eat a granola bar. If I wake up late, there's like an 80% chance I eat a granola bar, and otherwise, I'll make chilaquiles because it's awesome. And let's say I wake up on time 85% of the time. So part A of this is to construct a tree diagram that models the situation. And so this is very much a review of a couple weeks ago, so pause the video and make sure that you can get through A, maybe even B and C, and then we'll come back together and talk about part D. So first, real quick, I'm going to define some variables for myself. I'm going to define C to be chilaquiles. And I'm going to define T to be that I wake up on time. Okay, so now that I have that, I have this unconditional probability of 85% chance that I wake up on time. So on time is 85%, and not on time is 0.15. Then the problem said, if I wake up on time, the chilaquiles chance is 0.7, which means that the not chilaquiles, which means like granola bar, is 0.3. And if I wake up late, there's an 80% chance that I don't cook chilaquiles, and therefore a 20% chance that I do. Okay? Now that I've got all these branches, the next thing we do is we're supposed to multiply and figure out what these probabilities are that are at the end. So this top branch is 0.595. The second branch is 0.255. The third branch here is 0.03, and the final branch is 0.12. So I figured out what all these things are now. I'm basically done with part A. I've constructed the tree diagram. Part B of the problem asks, okay, what's the probability that I cook chilaquiles on a given morning? Well, looking at all of these things at the end, right, I remember what these represent. Right, this first one represents that I woke up on time and made chilaquiles. This one here is that I didn't wake up on time and made chilaquiles. So the probability that I cook chilaquiles is basically this one and this one added together. So that's 0.625. Now part C says, upon starting class, a student asks what I had for breakfast, and I respond that I had chilaquiles. What is the probability that I woke up on time? So I'm hoping that you guys see that this is a conditional probability. So upon starting class, a student asks what I had for breakfast. I respond that I had chilaquiles. So this right here is our given information, okay? So that's going to go in the denominator, 0.625, okay? That came from these things. Now, within that sample space, right, what is the probability that I woke up on time? Out of these two things, where's the one that came from me waking up on time? It's the top one. It's this 0.595. When I divide that on the calculator, I get this to be 0.925. So there's kind of this idea that, like, if I had chilaquiles this morning, I almost certainly woke up on time. So now we get to part D. Okay. Part D, in a standard 5-day school week, what is the probability that I cooked chilaquiles at least 3 times? And what I really hope you guys see here is that we had these first 3 questions that were all about what happens on one morning, and then suddenly the problem says, hey, so what about in a whole week? What about when I do 5 trials? What's the probability of me getting at least 3 times? Like, do you guys see how that just screams this binomial distribution? So if you're feeling up to it, try setting that one up and doing it on your own. If not, I'm going to go ahead and work through it right here. All right, so first I need a little bit of space here. Okay, so let's see here. Anytime we do these binomial things, we need to go through our steps, right? So step 1 is I need to define a new random variable. So there it is, right? At this point, I'm basically counting days, right? Let D be the number of days in a 5-day week that I cook chilaquiles, right? The next step, I state the distribution. D is distributed binomially with 5 trials and an individual probability of success. What is the probability that I cook chilaquiles on a given morning? Well, we figured that out. That was part B. So this is me using a previous part as I move forward. Okay. Next, I'm supposed to state the probability I'm trying to find. I want the probability that the number of days that I did this was at least 3, at least 3, at least 3 means 3 or 4 or 5. So I want the probability that D is greater than or equal to 3. That doesn't work very well with binomial CDF, so I'm going to do 1 minus the probability that D is the opposite of being greater than or equal to 3 would be less than or equal to 2. And now that's something I can put into the calculator as a binomial CDF. Calculator gave me that this was 1 minus 0.275, which gives me 0.725. So I hope that this lesson all made sense. I was really trying to go through a few ways that the IB problem can sort of like spice up these binomial distribution problems. So remember, if you've got questions, ask me, reach out. You got this.